Hello, class. Today we'll look at another application, which is radioactive decay. And this is the storyline. Radioactive substances decay by emitting radiation spontaneously. By doing so, we can see that, okay, if over time the substance is reducing in terms of its mass, we can talk about the rate of decay. Right, and the rate of decay is going to be proportional to what the substance is. All right, so the way we think about this is that rate of decay is determined in terms of the half-life of that substance. All right, so think about it this way: you have a substance and it's got a half-life, and the half-life is what we're calling the time that it takes that substance to decay to half of its original substance. So, for example, if you had in this problem here, they have this radioactive substance called radium 226, and its half life is 1600 years, meaning that after 1600 years, whatever amount that you initially started off with will be reduced by half. So, if you start off with 100 grams of that substance, by 1600 years, that substance would have reduced to 50. And then by 3200 years, that another half life has passed, that substance would have reduced to 50 divided by 2. That gives you 25. And then after another 1600 years has passed, you'd have to do 25 divided by 2 to get to half of that substance that is left. So you can, if you think about it intuitively, it kind of mimics what we looked at when we're looking at doubling time or tripling time. It's got a growth, a decay factor in that. That the decay factor is a half. All right. So if you think about it this way, if I have my final, went too fast. All right. If I have m of t, which is, we're going to use m of t instead of p or a, then I'm saying that I have my initial amount, m naught, and I know that by the half-life, I should have reached half of my substance. So I'm looking at this and going, this is 1/2. And by the half-life, so t over h, just as we did with the doubling time, where h is equal to the half-life. Okay, so now if you think about it, if I reach my half-life h, then this is going to be m naught 1/2 h over h, which is just what? M naught over 2. So indeed, the definition for a radioactive decay function is always going to be the initial times half raised to the t over h. You can also rearrange this by cleaning up the half as an exponent. So I end up getting mt is equal to m naught 2 to the negative 1 t over h, and that would become m naught 2 negative t over h. So both definitions are fine. Pick which one you feel you are comfortable using. But this is coming from an intuitive understanding that half of your substance is left once you've attained your half-life of that substance. All right. An alternative formula is, from the definition, radioactive substances emit radiations spontaneously. So we can think about it in terms of spontaneously, continuously kind of go together. So we can think about that formula that we derived when we looked at compounding continuously. Right? We can think about PERT, right? So when you think about PERT, when we looked at compounding continuously. That R was a relative growth rate. But in this case, we have a radioactive decay. It's decaying, and we have a rate of decay. So the R over here is a relative decay rate. Okay, so we can mimic this part for our use in this problem set here. So if I do that, I'm going to get m of t is equal to m naught e to the negative rt. All right, and it's negative because remember that r has to be negative for it to decay. So that's why we're putting the negative there. Okay. Now the question is, what is this relative decay rate? So we need to find it. All right, it's not going to be given to us. If it's given to you, fine. But in most cases, we'd have to find what that relative decay rate is when we are dealing with a radioactive decay. So one way to look at it is we do know what happens at the half-life. So if H is equal to T, that is the half-life, when I reach that half-life, this is supposed to be m naught e to the negative RH. But at that half-life, this mH is the same as m naught over 2. It's half of its original substance. So I end up with m naught e to the negative RH. And then from there, I can start solving for what that radioactive decay rate is supposed to be. So I end up getting 1/2 is equal to e to negative RH. Well, what I'm looking for is the r, which is an exponent. So the only way to kind of solve that problem is if we went through logarithms. So if I apply the ln on both sides, I got ln e to the negative RH. Well, I can see that this is ln 1 minus ln 2 if I apply my properties of logarithms. And then I can also do another property over here, drop the power down, ln e. Well, ln e is 1, so this becomes ln 1 minus ln 2 over negative h is equal to r. We also know that ln 1 is 0, so this becomes ln 2 over h is equal to r. So the relative decay rate when I am dealing with the radioactive decay problem is going to be ln 2 divided by the half-life h. All right. So you can see that we can write that definition, m of t is equal to m naught e to the negative ln 2 over h times t. So that becomes the second definition that we can mess around with when we think about it as a radioactive substance emitting radiation spontaneously, continuously. We can incorporate that E in our work, and that is where we end up with this fancy definition over here, which you need to know what the relative decay rate is, which is always going to be ln 2 over h. Okay. All right, so yeah, they talk about the two definitions. So we have this definition over here, and we have our intuitive understanding, which is m naught 1/2 t over h, or you can write it out as m naught 2 negative t over h. Okay, so let's look at this quick example over here, and let's see how we solve these problems. So it says you have a polonium-210, which has a half-life of 140. So H is 140. And then it's got a mass, m naught, which is 300. Okay. And they want us to write using the first definition, the more intuitive understanding. And then the second one says try to write it using the one that involves E. So if I set up A, m of t is equal to 300, 2 to the negative t over 140. And B is MT is equal to 300 e to the negative r t. So the only problem is I don't know what r is, but I can find what r is. R is what? ln 2 divided by the half-life. The half-life is 140, so I get ln 2 over 140. So I can write this as mt is equal to 300 e to the negative ln 2 over 140 times t. Okay. Let's look at C. So C says how long, find the mass remaining after 1 year. So we have a little unit conversion to do over here. The half-life is given us in days, but I'm asking you to find it in years. So you need to convert that to 365 days. So I'm looking at M 365 is the same as 300 E. Well, let's use the easy one. 300 2 raised to the negative 365 over 140. Let's see if we calculate that. I'm getting 9.24. All right, grams. Is it milligrams? Okay, I could have equally used the other definition too. And then D says, how long will it take the sample to decay to 200? So I'm looking at 200 is equal to 300, 2 to the negative t over 140. All right, so if I clean up the work, I got 2/3 is equal to 2 to the negative t over 140. And if you keep working, what I'm trying to solve is a power. So I need to use some natural logs to do this. I got 2/3 is equal to negative t over 140 ln 2. So t is the same as negative 140 ln 2/3 divided by ln 2. And when you do that and you calculate t is equal to 81.89. Okay. Alrighty. So let's check our answers to see. I think my solutions run over, but that's okay. So A was exactly the same as that. B, we have the same thing. If you calculate the ln, yeah, and you end up getting that same value that I had, right? I have ln. If we calculate that ln, we have ln if we calculate that ln to make sure we get the same, I got ln 2 divided by 140. You end up with that same answer. The way this is written is incorrect. So this is not right. It's supposed to be ln 2. all over 140. Okay. Alrighty, and then the last one is, well, C was when we're trying to do it with 365. Just got to be careful. Make sure you're checking your unit to make sure they're all in the same. And then the last one was to solve for the time, which is exactly what we did too. So we have that. Okay, and the last one, which we can do together over here, is it says sketch it. And the sketch shouldn't be that hard because we already know upfront what this graph is supposed to be. It's a radioactive decay, so we know that the graph is exponential and is decreasing from left to right. All we need is to set up some data points. So my first data point is already given to me. That is the initial. And then we also calculated at least the one for 365. So we can also find that. And then we can just connect things together so we can see that it's decreasing along from left to what? From left to right. All right. So you do have some data point to help you sketch a rough estimate of what that exponential decay graph should look like. Okay, so that is it. I will see you in the next video.